Hello, this is section 5.2 for Calc survey, and we're going to continue our discussion from 5.1, and we're going to talk about the definite integral. So we're going to kind of add some math notation into what we did in 5.1. So this actually is a problem from 5.1. So if t is time in hours since the start of a 20-hour period, a bacteria population increases at a rate. So here's our derivative they're giving us. And you might note increases at a rate given by, but it doesn't have the derivative notation, and that is okay. But you have to keep in mind this actually represents the derivative. Maybe it's the derivative of capital F of t, but you're going to have to be a little bit flexible with that notation. So, but this does represent, look, millions of bacteria per hour. It is a derivative. So it says make an underestimate of the total change in the number of bacteria over this period using intervals of size 4 hours. All right, so I started with 0, and it wants us to use intervals of 4. So that's from 4, 8, 12, 16, 20. Then I plugged these numbers into our derivative. That's those points on the curve. And it asks for an underestimate. So for each rectangle, you can kind of see the rectangles here. You're going to want to use the lower of the two sides. So for this first rectangle, you're going to pick 3. And that's what you can see over here. And then for this next rectangle, again, you're going to go with the lower of the two sides, which is the 4.6. That's the height. And you'll notice because it's an increasing function the whole time, it is the left estimate. So when you get to that last rectangle, you do end up throwing out that last set of data. All right. Then from there, you just add all those rectangles together, and here's your underestimate of the area under that curve. So we would estimate in that 20-hour period, this is our underestimate of 252 million bacteria. Okay. Now, the size of the intervals that we use to estimate the total area is known as your change of t. It's also the base length of each rectangle. And the number of subintervals used to estimate the total area is n. So in this case, we did 1, 2, 3, 4, 5 rectangles. Okay, so our change of t was 4 and n was 5. So says suppose we have a function f of t over the interval from a to b, then we divide the interval into n equal subdivisions, each of with change of t. So the change of t is b minus a over n. Now in this example, they told us the change of t. We went from there. But had they not, had instead they said 5 rectangles, then here's the b minus a, so the upper bound minus lower. So 20 minus 0 over 5 spits out the change in x, or the base length of each rectangle, which is 4. Now, to improve our estimate, we need to decrease the change in t. We're trying to make that change in t smaller and smaller and smaller, giving us more and more rectangles. That's the idea, which will increase the number of rectangles, what we just said. So in the last section, we showed how these are under and over estimates. These are also known as left-hand and right-hand estimates, and I told you that in the last section. It's actually easier when it says use a left estimate, because then you don't have to worry about the function increasing and decreasing and maybe potentially having to switch sides to stay with the underestimate or vice versa. So if it says left-hand estimate, you're literally going to use the left side of each rectangle to determine the height. And then if it's the right hand, then the other way, you're going to use the right hand of each rectangle. So when it's the left hand, you throw out the last set of data, because that would give you an extra rectangle you don't want. When it's the right hand, you actually start one over, so you end up throwing out the first set of data. Okay. Now, it gets a little, we're going to use some math notation here, but left-hand sum, if you look carefully, it's just the rectangles. So when you do the left, you notice it's f of t initial, you're using that first initial data, times the change in t, that's the base length. And you keep going, and then you end up stopping one short. So f of t sub n minus 1 times the change in t. And if you use summation notation, there it is. Remember, that's where you start, I equals 0, and you end at n minus 1. And then that's just the height of your rectangle times the base length. Now, if you do the right-hand sum, same idea, but now you start one data over. You start with the first set of data instead of the t initial. And then you get to stop at t sub n. And that's what this notation is. Now, we could keep using this notation, and in Calc AB, we like the right-hand notation because if you remember, you had some summation formulas that were very helpful with I and I squared and I cubed. So we go into that with Calc AB. So we like the right-hand estimate because I starts at 1. But this notation, there's a much better notation we like to use. So what we're going to do, we end up getting rid of the sigma notation, and it's replaced by an old-fashioned S, and the change of t is replaced by a dt. So basically we're going to take this notation and we're going to create an integral symbol here, an elongated S. F of t, that's your, we call that an integrand. That's your integrand. And then dt. And every time you write an integral symbol, there has to be some type of change of, usually it's change in x, so dx, dt, but you'll never have an integral without a dt or a dx or whatever the variable is you're doing the antiderivative with respect to. I know you don't know what that means, but we will get into that in the future. Okay. Now, just a quick little fun fact. Do you remember back when we did derivatives? And we had y equals 2x squared. And I said, do the derivative. And you wrote y prime. But I also said, hey, you could also write the derivative as dy dx equals 4x. Well, if you multiply over the dx, we can write it this way as a differential equation. And if you notice, that's the derivative times dx, which is exactly what's there. Okay, so the derivative times dx dt, whatever the variable is. Now, we're eventually going to start to call this, we have a definite integral and an indefinite integral. But the idea is, if you have these rectangles and you have infinitely many of them, that's how we're jumping from this notation of having just maybe 5, 10 rectangles to, if we have infinitely many rectangles, we can now write this notation this way. Right. Now, if you are really interested in this, come see me. In Calc AB, we go a lot more in depth with this notation and all of that. This is kind of just a big jump right here. But if you want some more information, come see me. All right, so suppose f is continuous from a to b. The definite integral of f from a to b can be written this way. So this is new to you. This notation means we want the area under this curve, that function right there, from a to b. And here's where it gets a little more of the stuff we do in AB. So this notation is the same as this notation. And same thing here. This is the left and right. Okay, and those rectangles we talked about earlier with the left and right, there can also be called a Riemann sum. And F's called the integrand. I already told you that. So this is the integrand here. A and B are called the limits of integration. You might also hear me call them the bounds of integration. But we're not going to be using this notation. I know you're very sad to learn that, but we're going to use this notation because it's much nicer. Okay. So again, I can't emphasize this enough. When you see this, it means the area under this function, this curve, to the x-axis from A to B. That's what that means. All right, so compute this and represents the integral as an area. So we just used our calculator. You can use your calculator to find this. In class, we'll talk about it. But if you go to the calculator, go to the menu, calculus, find definite integral, and that's what you'll type in. Now, I went ahead and graphed. So t squared is a parabola. So I graphed it. And we're finding the area from 1 to 3. So I went ahead and shaded that region in. And 8.67 is what the calculator spits out when you type this in. And that's the area under that curve. Now, that's an amazing leap we just took. We went from being able to just do some rectangles, get an idea, to now using this notation in your calculator, it actually gives you the area under the curve. It's still technically an approximation, but it's an immeasurably close approximation to the area under that curve. because your calculator is using infinitely many rectangles to get that estimation. All right, so here's another one. Use a left-hand Riemann sum with 3 intervals to estimate the value of this. So this is your new notation. That's the function. That's your derivative. And that's going to give you the heights of each rectangle. So notice how you're going to do this is I'm going to start with the lower bound. So notice I put that as the first x value here. Now if it wants 3 intervals, that means it wants 3 rectangles. So use your b minus a divided by n to figure out the change in x. What's the base length of each rectangle? So that's how we're getting this answer here. So we want 3 rectangles, and that change in x or change in t is 3. So start with the lower bound in your table, and I'm going to add 3 each time. So 3 plus 3 plus 3, and then stop when you get to the upper bound. Now plug these x values into your derivative here to get the heights. So that's where these numbers are coming from. And it says to use a left-hand Riemann sum. So we're going to start from the left, and we've created 1, 2, 3 rectangles. And I'm going to use the left of each one to give me the heights. And remember, we always end up throwing out a set of data. But that's where this is coming from. So this is the base length of each rectangle times the height. Base times height. And that then gives us our left-hand Riemann sum. Okay. All right, let's try another one. Or this is actually a cool little lesson closer. So 3 people compute. So here's how you read this. The integral from 1 to 3 of 1 over t dt. That's how you read that out loud. And got the answers of 0.023, 11.984, and 1.526. How do you know all of these are wrong? All right. So I went ahead and sketched it. 1 over t kind of looks like this. That's the graph, a rough sketch. I'm interested from 1 to 3, and I shaded that region under the curve. That's the area I'm trying to find, or what the 3 areas these people tried to estimate. Okay, now I'm trying to disprove all of them. So what I did is I just used one big rectangle. So if you do the left side, I'm going to make base length 2, and the left side of that rectangle, the height is 1. So that's where this 1 times 2 is coming from. That's the left estimate of the area under that curve, and you get a big 2. So already you can throw out that 11.984. That is over my overestimate. It is obviously wrong. Okay, then I switched and did the right estimate. So I used the right side. So the point on the curve, that's the height, using the right estimate. And you can see that's going to give me 2 times 1/3. So that's where this is. You get 0.67. Well, that's an underestimate, and that 0.023 is under my underestimate. So again, that's also way wrong. So the first 2 are ruled out. I got this last one though. And notice that 1.526 falls between my 2 answers. So let's average and see what happens. So when you average these 2 together, so I add, divide by 2, you get 1.3 repeating. And you might still say, oh, I don't really still have enough, but you do. Because if you come over here, technically averaging these together is giving you this trapezoid here. That's the area of this trapezoid. And if you notice, because it's a concave up function, the area of that trapezoid happens to be a slight overestimate. And if 1.3 is an overestimate, 1.5 is bigger than that, so it can't be right. Okay. Now, had I used more rectangles, it would have just given me better answers to disprove these answers. But okay. So the big idea, especially this example, you're going to have a couple of these in your homework where it's going to tell you, and it's hard because you can type this in your calculator and get the answer, but that's not what they want. You have to do the number of rectangles. You have to use that b minus a over n. You'll have to be really careful and make sure you practice these, okay? And don't worry about this sigma notation. You're not going to see that again. It's just good for you to see where this integral notation has come from. Okay, Please do your homework on this stuff. Let me know if you have any questions.